So in this video we are discussing about source-free parallel RLC circuit. Source-free parallel RLC circuit. So I am going to consider a parallel RLC circuit shown in the figure. It means I will be having resistor, inductor and capacitor connected in parallel. The initial current I0 through the inductor will be considered as I0. Okay, 1 by L minus infinity to 0 V of t dt. Okay, so this is the initial current, and initial current across the capacitor is V0, V of 0, which is it can be written as V0. So three elements are in parallel. Definitely there will be same voltage across all of them. Okay. So next we are going to apply KCL to any of the node. It can be a top node or it can be a bottom node. So whichever node you choose, you just apply. So if it is applied to the bottom node, okay, what I will get? So IR is a current flowing through a resistor, I0 is a current, or IL is a current flowing through the inductor, and IC is a current flowing through the capacitor. Okay, so we can write it as IR plus IL plus IC equal to 0. Okay, I am assuming this node. So IR is a current entering, IL is a current entering, and IC is a current entering. Okay, so IR can be represented as V by R. So using Ohm's law, V equal to IR. So I equal to V by R. So I can represent in V by R. And then current voltage relationship of the inductor is 1 by L minus infinity to t V dt. Current voltage relationship. And then current voltage relationship for the capacitor is C dV by dt. C dV by dt. Okay. So to remove the integral, I am going to take I am going to differentiate this equation with respect to time. I am going to differentiate this to remove this integration. Okay, so what I will get? V by R dV by dt. Sorry, 1 by R dV by dt. V will be differentiated. So 1 by R dV by dt plus. So this integration will be removed. So 1 by L integration of V dt can be written as V, and then already dV by dt is there. So it will be differentiated one more time. It will be second order. So d square V by dt square. C d square V by dt square equal to 0. So I am going to divide by C. So I will get 1 by RC, 1 by LC, and this C will be cancelled. So we will get d square V by dt square plus 1 by RC dV by dt plus 1 by LC into V equal to 0, which is equation number 4. Okay, I am mentioning it as equation number 4. So remember this equation. So now similar to what we discussed earlier, I am going to consider d by dt equal to S. Okay, the same thing we have done for series RLC also, natural response of series RLC. So for the parallel RLC we are doing the same thing. D by dt can be represented as S. So the equation number 4 becomes S square, because d square by dt square can be written as S square, and d by dt can be written as S. So 1 by RC ds plus 1 by ELC equal to 0, which is equation number 5. Okay, the roots are S12 will be equal to minus 1 by RC plus or minus root of 1 by 2 RC whole square minus 1 by LC. So this can be represented as S12 equal to minus alpha plus or minus root of alpha square minus omega naught square. So one thing you have to note down, the alpha X formula for the series RLC and parallel RLC are different. So here the alpha equal to 1 by 2 RC and omega naught equal to 1 by root LC. So omega naught is obviously same for both, but alpha is different for series and parallel RLC, so keep a note of it. Okay, so here the alpha is equal to 1 by 2 RC. So the equation number 5 can be written as S square plus 2 alpha S 1 by RC. Okay, so will be replaced with alpha, 2 alpha. Okay, S square plus 2 alpha S plus omega naught square equal to 0. Okay, here we are dealing with voltage. Okay, if you see the equation for three cases, underdamped, overdamped and critically damped, okay, it will be same. but instead of current here we'll be using voltage. Okay, there in series the current was same, here the voltage is same. So V of t equal to A1 e power S1t plus A2 e power S2t. This is the equation of the differential equation. Okay, this is a solution for the differential equation. Okay, now let us see the three cases. When alpha is greater than omega naught, I will say overdamped case. In overdamped case, I will take the equation as it is. The voltage equation V of t equal to A1 e power S1t plus A2 e power S2t. So write down this formula now. You have to make a note of alpha formula, omega naught formula, and for overdamped case. What is overdamped case? Alpha should be greater than omega naught. In that case, what is the equation for V of t? In that case, what is the equation for V of t? V of t equal to A1 e power S1t plus A2 e power S2t. Okay. So next, critically damped case, alpha will be equal to omega naught. For the critically damped case, alpha will be equal to omega naught. Okay. So in that case, I will be considering the same equation which we written for the current in series RLC. Instead of I of t, we have V of t. So V of t equal to A1 A2t e power minus alpha t. So kindly refer the formulas and remember. Okay, it is not possible to remember all the formulas, so refer it. Okay, so compare the formulas and remember, and based on the requirement. Remember based on the requirement. And the last case is underdamped case, which is alpha less than omega naught. Okay, when alpha is less than omega naught, okay, I am going to get. So all these derivations we have done in series RLC circuit, which is lecture 1. Okay, in unit 4. Okay, you can refer to lecture 1 in unit 4, which is available in the description. Okay, so we'll be getting this equation V of t equal to e power minus alpha t A1 cos omega dt plus A2 sin omega dt. This is the equation we'll use for finding the voltage. Okay, for finding the voltage. The constant A1 and A2 will be calculated based on. Okay, in the series RLC I used B1 and B2. Here we are using A1, A2. The constant name doesn't matter. You can use B1, B2 also here. It doesn't matter. Okay. So here the initial condition we need is V of 0 and dV of 0 by dt. So from the equation 3, so we have V by R. Instead of V, I am writing V naught. V naught by R. Okay, I have 1 by C integral of I dt. Okay, that can be represented as I naught. Okay, I will show that. So 1 by L minus infinity to t V dt. So that can be represented as I naught. Next, C dV by dt can be represented as C dV naught by dt. C dV by dt can be written as C V naught by dt. V naught means V of 0. Okay, V naught means V of 0. Okay. So now I need to know the first derivative dV of 0 by dt. So I can take remaining things to the other side. So dV 0 by dt is equal to minus V naught by R minus I naught by C. So this formula also you should know. So dV naught by dt equal to minus, okay, better to take this. So minus of V naught plus I naught R by RC. Okay. So anyone of this, please remember. Okay, this we need to use for finding the constants. To find the constants. Okay. So we'll discuss the problem in next video. Thank you.